Today I'm going to continue my series on data structures by talking about hash tables. Now, as I mentioned earlier, I started looking into data structures because I was curious about the prospects of people who go to programming boot camps or coding boot camps, what kind of prospects they had in the employment field. And I found that they were being asked about data structures, which is something that they did not learn about in the boot camps. So I decided to find out what data structures were. I found out that I was already familiar with some data structures because I had worked with them in file systems, and I looked deeper to find out what I could learn about data structures. And in my research, about all I could find was abstract theory. So it took me a while to figure out what they were trying to explain, and my experience is that if I'm reading something and I'm having trouble understanding it, the person explaining it is leaving something critical out and may not really understand it themselves. So a lot of these people talking about data structures are reading scripts or simply repeating something they read or saw somewhere else, and they don't really understand them themselves. And I'm pretty sure about that because I understand what's going on at this level in computers, and a lot of people don't. So in my video on B-trees, I mentioned that I needed to learn about hash tables, and as soon as I did, I would make a video on them. And doing my research on hash tables, of course, all I found was abstract theory, nothing about how they're implemented, and it took me a while to put the pieces together to figure out how a hash table works. So this is my understanding of hash tables and how I would implement one if I were making one. Now, these data structures that we're talking about are something you don't see as a database manager. These are things that are done behind the scenes in the programs and in the operating systems. So it's not something that you would work with as a database manager, but something that you would if you were writing a program that handled a database. Are you going to write a program that is a database manager? Probably not, but there are other programs you might write that have to handle data, and you might end up having to work with data structures. So let's take a look at how a hash table works. First, let's take a look at the problem that needs to be solved. So we have a database, and I'm going to represent that as a table as usual. A database can be thought of as like a big spreadsheet. So a lot of people handle their database management. If it's a small database, they just simply put it into a spreadsheet. But if you have a lot of data or need to manipulate that data or present that data in certain ways, a database manager is a much better solution. Because we have, if you think of the spreadsheet, we have rows of data and columns. So it looks something like this. We have, like names, addresses, phone numbers, etc. All the information we have about that person pertinent to the organization that is using the data. So we might have a long row of, name, address, phone, favorite color, who knows what we might have out in this database that's useful, and each row is for a different person or different entity of some sort. And so we have something like, and please excuse me for looking off screen here because I had to make a lot of preparation to make this understandable. So I'm going to already have some names picked out. Let's see, we have Vera, and I'm going to use all capital letters, and you'll see why in a moment. So we have Vera and Gary and Zeke. Why such a weird name? You'll see that I picked these names carefully to help explain how a hash table works. And Bob. And we need a couple more rows of data here. And what do we have? We have Jan and Paul. If I can do that. Paul. And so here we have 6 people in this database. Now a real database would of course probably have hundreds or thousands of people, but I need to keep this small to be able to put it on the board and explain it. So name, address, phone number, favorite color, whatever. First person, Gary. Might want to put the Y there for Gary. So Vera, name, address, phone number, Gary, name, address, phone number, favorite color, etc. All the different information on the different rows. And the database manager will pull out rows of data as we ask for them, present them in a useful way, allow us to make changes and put them back, or whatever the database manager needs to do. So 6 rows here, name, address, phone, etc. Now, the problem that needs to be solved is searching for data. Now, with just 6 names, that's not really much of a problem, but when you have thousands of them, that can become a problem. As I explained in the earlier video on B-trees, and I recommend that you watch that video. I'll explain some things there that I only gloss over here, so I do recommend you watch the video on B-trees and then come back if you have not. But anyway, to do a search, we humans can see the whole picture, and we are pattern recognizers. We can grasp onto a pattern pretty quickly, and if we have a small, even a big table, we can look through for a name, and pick it right out. Computers can't work that way. They can only look at bytes of data and do comparisons. So it has to go through the database byte by byte. So each letter of the alphabet is stored in memory as a number, and the numbers used are in the ASCII code. We've talked about that before. For example, the letter A is stored as 01000001. The letter B, that's a capital A. Capital B is 01000010. Or in decimal, this would be 65, and this would be 66. That will become useful in a few moments. So each of these is stored in memory as a number, and the computer can go, let's say we decide to look for Bob. So we have to look letter by letter. Is that a B? No. So now it knows it can skip to the next name, so it skips all this data in memory to the next one, next record down, or next row down. Sometimes these are called records, sometimes they're called rows. It depends on who's talking. Goes to the next record. Is that a B? Nope. Is that a B? Nope. Ah, is that a B? Aha, now let's took the next letter. Is that an O? Yes, it is an O. Let's say if there was Bill. Is that a B? It comes out I. Nope, have to skip to the next one. So I have to look letter by letter, and that's fairly time consuming as it goes down. And if you can imagine, if this is thousands of pieces of data, it can take quite a while, especially if I'm looking for the name that happens to be the last one in the database. Is going to have to go and check every single name to find that. So searching is a bit of a problem. In my previous video on B-trees, I showed a way to fix that. First of all, we alphabetized the table. Now, that doesn't help in its own right, but by alphabetizing it, we were able to do a divide and conquer search. So we were able to go into the middle of the table and say, is this Bob? No. Okay, is Bob higher or lower? Bob is higher, so let's go split the difference. Is this one Bob? No. Is Bob higher or lower? Let's split the difference. Is this one Bob? Nope. Higher or lower? Split the difference and keep going until you eventually zero in on the entity you are looking for. And that improves the search by about an order of magnitude, about a factor of 10, and speeding up the search. One problem there is if we have to alphabetize these, that's an awful lot of data to alphabetize. I mean, we have to move the entire rows of data, and that has to be done a byte at a time, and we have to move it all out somewhere else to make room, move things here and there, move things back. Sorting things physically can be quite an arduous task, especially if we have lots and lots of data in each row. So rather than sorting the entire row of data, what we'll do is make an index with just the names. And so we take the names out and sort them. Let's put these in alphabetical order now, like Bob and Gary. I have this already done, so I don't have to think about it. Jan and Paul and Vera and Zeke. And once we've done that, we can do that divide and conquer search. Kind of hard to show here with only 6 names, but we would go into the middle, see if that one's the right one, then split the difference either higher or lower until we zero in on it. But then we realized that we could save the calculating power of knowing where to go in by putting a number after each of these. So we know if we search here and that's not the right one, well, if it's higher, we're going to go to a particular name. If it's lower, we're going to go to a particular name. And once again, watch my video on the B-trees to understand this fully. But we would put a pointer to the next name. So instead of having to calculate where to go, we just have a couple of pointers that basically says, if you need to go higher, we want to split the difference. Well, what name is that? And a pointer to that name, just a number that points up to that name. and another number that points down if we need to go down. You have a different pointer. Once again, I don't want to go into details on that here, so watch the video on B trees to understand how the divide and conquer search works and how converting that into a B tree makes that search much more efficient. Okay, so that improves that a lot, but is there a better way to improve it? And there is, and that is called a hash table. So let's explain what a hash is. We hear about hashes, we usually think about cryptological hashes, which are very complex algorithms that will take any number of characters and produce a set number of digits that if you calculate that particular set of data, it will always create the same digits. But it's not reversible. You can't figure out what you encoded or what you hashed from the hash. If you have the hash, you can't figure out what created the hash. So that's a non-reversible, it's not really an encryption, it's just a code that represents the entity. And if you hash that entity or run it through that algorithm, you always get the same code. And this is often used for cryptological purposes to obscure things, such like obscure passwords. So let's say someone's logging into a website and they have a password. Well, you don't want to store their password because if someone gets into your server, they could actually get the passwords. So you hash the password and store the hash. It's a little more complicated than that because you don't want to have multiple sites hashing the same password the same way. Then you could get clues to figure out what the hashes and the password pairs were. So you want to do a little more than that, but the idea is take your password, run it through a hashing algorithm and store that hash. Then the next time they log in, you run it through that algorithm again. They type in their password, you run it through the algorithm, you get the hash, you compare that to the stored hash, and if they match, then they typed in the right password. This is a little different purpose, so we don't need to have a complex cryptological hash algorithm. We can use something much simpler, and what I'm going to use is a checksum, which means I'm just going to take the codes that represent each letter and just add them up until I get a sum. Well, a little more complex than that because what I want is a 2-digit decimal hash. So no matter what I do, no matter how long the name is, I stuck to 3 and 4 letter names here, but no matter how long the name is, I want to end up with a number between 0 or from 0 to 99. And so what I'm going to do, let's say for example, I'm going to hash Vera up here. So Vera has an ASCII code of 86, 69, 82, and 65. As I mentioned earlier, the capital letter A is represented by the number 65. So there's a V, there's an E, there's an R, there's an A. Now what I want to do is simply add these together. So 88 plus 69 gives me 155. But I want to keep this to a number under 100. So what I'm going to do is just throw out the carry over here, leaving me with 55. Now I'm going to add that to 82. So that gives me 137. Once again, I want to keep this to a 2-digit number, so I just throw out the 1 again. So each time I add them together, if I get a number higher than 100, I throw out the 1, or I subtract 100 from it, however you want to look at it. So that gave me 37. Now I have to add the last letter, which is 65. That's going to give me 37 plus 65 gives me 102. Throw out the 1, that gives me 2. So the hash for Vera ends up being 2. And I'm going to do this for all of my entities over here. I have these alphabetized, but they don't need to be. Bob is going to be 11. Gary is going to be 7. Jan is 17. Let's see, Paul is 6. And we're losing Zeke here. And Zeke is 3. So those are the decimal numbers that I get by running each of these through a checksum. So here are my hash values.